Introduction to Generative AI. Don't know what that is? Then you're in the perfect place. In this course, I'll teach you 4 things: how to define generative AI, explain how generative AI works, describe generative AI model types, and describe generative AI applications. But let's not get swept away with all that yet. Let's start by defining what generative AI is first. Generative AI has become a buzzword, but what is it? Generative AI is a type of artificial intelligence technology that can produce various types of content, including text, imagery, audio, and synthetic data. But what is artificial intelligence? Since we're going to explore generative artificial intelligence, let's provide a bit of context. 2 very common questions asked are, what is artificial intelligence, and what is the difference between AI and machine learning? Let's get into it. So, one way to think about it is that AI is a discipline, like how physics is a discipline of science. AI is a branch of computer science that deals with the creation of intelligent agents and are systems that can reason, learn, and act autonomously. Are you with me so far? Essentially, AI has to do with the theory and methods to build machines that think and act like humans. Pretty simple, right? Now let's talk about machine learning. Machine learning is a subfield of AI. It is a program or system that trains a model from input data. The trained model can make useful predictions from new, never-before-seen data drawn from the same one used to train the model. This means that machine learning gives the computer the ability to learn without explicit programming. So, what do these machine learning models look like? 2 of the most common classes of machine learning models are unsupervised and supervised ML models. The key difference between the 2 is that with supervised models, we have labels. Labeled data is data that comes with a tag, like a name, a type, or a number. Unlabeled data is data that comes with no tag. So, what can you do with supervised and unsupervised models? This graph is an example of the sort of problem that a supervised model might try to solve. For example, let's say you are the owner of a restaurant. What type of food do they serve? Let's say pizza. Wait, dumplings. No, pizza. I love pizza. Anyway, you have historical data of the bill amount and how much different people tipped based on order type, pickup, or delivery. In supervised learning, the model learns from past examples to predict future values. Here, the model uses the total bill amount data to predict the future tip amount based on whether an order was picked up or delivered. Also, guys, tip your delivery drivers. They work hard. This is an example of the sort of problem that an unsupervised model might try to solve. Here, you want to look at tenure and income, and then group or cluster employees to see whether someone is on the fast track. Nice work, blue shirt. Unsupervised problems are all about discovery, about looking at the raw data and seeing if it naturally falls into groups. This is a good start, but let's Unsupervised problems are all about discovery, about looking at the raw data and seeing if it naturally falls into groups. This is a good start, but let's go a little deeper to show this difference graphically, because understanding these concepts is the foundation of your understanding of generative AI. In supervised learning, testing data values, x, are input into the model. If the predicted test data values and actual training data values are far apart, that is called error. The model tries to reduce this error until the predicted and actual values are closer together. This is a classic optimization problem. So, let's check in. So far, we've explored the differences between artificial intelligence and machine learning and supervised and unsupervised learning. That's a good start. But what's next? Let's briefly explore where deep learning fits as a subset of ML methods, and and then, I promise, we'll start talking about Gen AI. While machine learning is a broad field that encompasses many different techniques, deep learning is a type of machine learning that uses artificial neural networks, allowing them to process more complex patterns than machine learning. Artificial neural networks are inspired by the human brain. Pretty cool, huh? Like your brain, they are made up of many interconnected nodes, or neurons, that can learn to perform tasks by processing data and making predictions. Deep learning models typically have many layers of neurons, which allows them to learn more complex patterns than traditional machine learning models. Neural networks can use both labeled and unlabeled data. This is called semi-supervised learning. In semi-supervised learning, a neural network is trained on a small amount of labeled data and a large amount of unlabeled data. The labeled data helps the neural network to learn the basic concepts of the task, while the unlabeled data helps the neural network to generalize to new examples. Now, we finally get to where generative AI fits into this AI discipline. Gen AI is a subset of deep learning, which means it uses artificial neural networks, can process both labeled and unlabeled data using supervised, unsupervised, and semi-supervised methods. LLMs are also a subset of deep learning. See? I told you I'd bring it all back to Gen AI. Good job, me. Deep learning models, or machine learning models in general, can be divided into two types: generative and discriminative. A discriminative model is a type of model that is used to classify. Good job, me. Deep learning models, or machine learning models in general, can be divided into two types: generative and discriminative. A discriminative model is a type of model that is used to classify or predict labels for data points. Discriminative models are typically trained on a dataset of labeled data points, and they learn the relationship between the features of the data points and the labels. Once a discriminative model is trained, it can be used to predict the label for new data points. A generative model generates new data instances based on a learned probability distribution of existing data. Generative models generate new content. Take this example. Here, the discriminative model learns the conditional probability distribution, or the probability of y, our output, given x, our input, that this is a dog, and classifies it as a dog and not a cat, which is great because I'm allergic to cats. The generative model learns the joint probability distribution, or the probability of x and y, p x of y, and predicts the conditional probability that this is a dog and can then generate a picture of a dog. Good boy. I'm going to name him Fred. To summarize, generative models can generate new data instances, and discriminative models discriminate between different kinds of data instances. One more quick example. The top image shows a traditional machine learning model which attempts to learn the relationship between the data and the label, or what you want to predict. The bottom image shows a generative AI model which attempts to learn patterns on content so that it can generate new content. So, what if someone challenges you to a game of, is it Gen AI or not? I've got your back. This illustration shows a good way to distinguish between what is Gen AI and what is not. It is not Gen AI when the output, or Y, or label, is a number or a class, for example, spam or not spam, or a probability. It is Gen AI when the output is natural language, like speech or text, audio, or an image, like Fred from before, for example. Let's get a little mathy to really show the difference. Visualizing this mathematically would look like this. If you haven't seen this for a while, the y equals function of x equation calculates the dependent output of a process given different inputs. The y stands for the model output, the f embodies the function used in the calculation, or model, and the x represents the input, or inputs, used for the formula. As a reminder, inputs are the data like comma-separated value files, text files, audio files, or image files, like Fred. So, the model output is a function of all the inputs. If the y is a number, like predicted sales, it is not generative AI. If y is a sentence, like define sales, it is generative, as the question would elicit a text response. the response would be based on all the massive large data the model was already trained on. So, the traditional ML supervised learning process takes training code and labeled data to build a model. Depending on the use case or problem, the model can give you a prediction, classify something, or cluster something. Now, let's check out how much more robust the generative AI process is in comparison. The generative AI process can take training code, labeled data, and unlabeled data of all data types and build a foundation model. The foundation model can then generate new content. It can generate text, code, images, audio, video, and more. We've come a long way from traditional programming to neural networks to generative models. In traditional programming, we used to have to hard code the rules for distinguishing a cat. Type, animal, legs, for, ears, to, fur, yes, likes, yarn, catnip, dislikes, Fred. In the wave of neural networks, we could give the network pictures of cats and dogs and ask, is this a cat? And it would predict a cat, or not a cat. What's really cool is that in the generative wave, we, as users, can generate our own content, whether it be text, images, audio, video, or more. For example, models like PaLM, or Pathways Language Model, or Lambda, or Language Model for Dialogue Applications, ingest very, very large data from multiple sources across the internet and build foundation language models we can use simply by asking a question, whether typing it into a prompt or verbally talking it into the prompt itself. So, when you ask it, what's a cat? It can give you everything it has learned about a cat. Now, let's make things a little more formal with an official definition. What is generative AI? Gen AI is a type of artificial intelligence that creates new content based on what it has learned from existing content. The process of learning from existing content is called training and results in the creation of a statistical model. When given a prompt, Gen AI uses this statistical model to predict what an expected response might be, and this generates new content. It learns the underlying structure of the data and can then generate new samples that are
Generative language models. Generative language models learn about patterns in language through training data. Then, given some text, they predict what comes next. Mountains and you see. The fuck? Watch that shit, because that shit is fucking cancer. Let's see. YouTube short titles or see that shit. I want to see that shit. You know what? Let's go to the fucking source. YouTube.com. We're gonna see what the best short titles are. And we are gonna go from there. Shorts. POV in Italian reads to American children books. Every black character's hairstyle. Yeah, I see that. Hey, what's up? Alright. You have a good one too.
similar to the data it was trained on. Like I mentioned earlier, a generative language model can take what it has learned from the examples it has been shown and create something entirely new based on that information. That's why we use the word generative. But large language models, which generate novel combinations of text in the form of natural-sounding language, are only one type of generative AI. A generative image model takes an image as input and can output text, another image, or video. For example, under the output text, you can get visual question and answering, while under output image, an image completion is generated, and under output video, animation is generated. A generative language model takes text as input, and under output video, animation is generated. A generative language model takes text as input and can output more text, an image, audio, or decisions. For example, under the output text, question and answering is generated, and under output image, a video is generated. I mentioned that generative language models learn about patterns in language through training data, then give some text, then predict what comes next. Thus, generative language models are pattern matching systems. They learn about patterns based on the data you provide. Check out this example. Based on things it's learned from its training data, it offers predictions of how to complete this sentence. I'm making a sandwich with peanut butter and jelly. Pretty simple, right? Here's the same example using Bard, which is trained on a massive amount of text data and is able to communicate and generate human-like text in response to a wide range of prompts and questions. See how detailed the response can be? Here's another example that's just a little more complicated than PB&J's. The meaning of life is, and even with a more ambiguous question, Bard gives you a contextual answer and then shows the highest probability response. The power of generative AI comes from the use of transformers. Transformers produced the 2018 revolution in natural language processing. At a high level, a transformer model consists of an encoder and decoder. The encoder encodes the input sentence and passes it to the decoder, which learns how to decode the representations for a relevant task. Sometimes, transformers run into issues though. Hallucinations are words or phrases that are generated by the model that are often nonsensical or grammatically incorrect. See, not great. Hallucinations can be caused by a number of factors, like when the model is not trained on enough data, is trained on noisy or dirty data, is not given enough context, or is not given enough constraints. Hallucinations can be a problem for transformers because they can make the output text difficult to understand. They can also make the model more likely to generate incorrect or misleading information. So, put simply, hallucinations are bad. Let's pivot slightly and talk about prompts. A prompt is a short piece of text that is given to the LLM as input, and it can be used to control the output of the model in a variety of ways. Prompt design is the process of creating a prompt that will generate the desired output from a large language model, LLM. Like I mentioned earlier, generative AI depends a lot on the training data you have fed into it. It analyzes the patterns and structures of the input data and thus learns. But with access to a browser-based prompt, you, the user, can generate your own content. So let's talk a little bit about the model types available to us when text is our input, and how they can be helpful in solving problems, like never being able to understand my friends when they talk about soccer. The first is text-to-text. Text-to-text models take a natural language input and produce text output. These models are trained to learn the mapping between a pair of texts, for example, translating from one language to another. Next, we have text-to-image. Text-to-image models are trained on a large set of images, each captioned with a short text description. Diffusion is one method used to achieve this. There's also text-to-video and text-to-3D. Text-to-video models aim to generate a video representation from text input. The input text can be anything from a single sentence to a full script, and the output is a video that corresponds to the input text. Similarly, text-to-3D models generate three-dimensional objects that correspond to a user's text description for use in games or other 3D worlds. And finally, there's text-to-task. Text-to-task models are trained to perform a defined task or action based on text input. This task can be a wide range of actions, such as answering a question, performing a search, making a prediction, or taking some sort of action. For example, a text-to-task model could be trained to navigate web UI or make changes to a dock through the GUI. See, with these models, I can actually understand what my friends are talking about when a game is on. Another model that's larger than those I mentioned is a foundation model, which is a large AI model pre-trained on a vast quantity of data, designed to be adapted or fine-tuned to a wide range of downstream tasks, such as sentiment analysis, image captioning, and object recognition. Foundation models have the potential to revolutionize many industries, including healthcare, finance, and customer service. They can even be used to detect fraud and provide personalized customer support. If you're looking for foundation models, Vertex AI offers a model garden that includes foundation models. The language foundation models include Palm API for chat and text. The vision foundation models include Stable Diffusion, which has been shown to be effective at generating high-quality images from text descriptions. Let's say you have a use case where you need to gather sentiments about how your customers are feeling about your product or service. You can use the classification task sentiment analysis task model. Same for vision tasks. If you need to perform occupancy analytics, there is a task-specific model for your use case. So, those are some examples of foundation models we can use, But can Gen AI help with code for your apps? Absolutely. Shown here are generative AI applications. You can see there's quite a lot. Let's look at an example of code generation shown in the second block under code at the top. In this example, I've input a code file conversion problem, converting from Python to JSON. I use Bard and insert into the prompt box. I have a pandas data frame with 2 columns, one with the file name and one with the hour in which it was generated. I am trying to convert it into a JSON file in the format shown on screen. Bard returns the steps I need to do this, and the code snippet. And here my output is in a JSON format. Pretty cool, huh? Well, get ready, it gets even better. I happen to be using Google's free browser-based Jupyter Notebook and can simply export the Python code to Google's Colab. So, to summarize, Bard code generation can help you debug your lines of source code, explain your code to you line by line, craft SQL queries for your database, translate code from one language to another, generate documentation and tutorials for source code. I'm going to tell you about 3 other ways Google Cloud can help you get more out of generative AI. The first is Vertex AI Studio. Vertex AI Studio lets you quickly explore and customize generative AI models that you can leverage in your applications on Google Cloud. Vertex AI Studio helps developers create and deploy generative AI models by providing a variety of tools and resources that make it easy to get started. For example, there is a library of pre-trained models, tool for fine-tuning models, a tool for deploying models to production, community forum for developers to share ideas and collaborate. Next, we have Vertex AI, which is particularly helpful for all of you who don't have much coding experience. You can build generative AI search and conversations for customers and employees with Vertex AI Search and Conversation, formerly Gen AI App Builder. Build with little or no coding and no prior machine learning experience. Vertex AI can help you create your own chatbots, digital assistants, custom search engines, knowledge bases, training applications, and more. And then we have Palm API. Palm API lets you test and experiment with Google's large language models and Gen AI tools. To make prototyping quick and more accessible, developers can integrate Palm API with MakerSuite and use it to access the API using a graphical user interface. The suite includes a number of different tools, such as a model training tool, a model deployment tool, and a model monitoring tool. And what do these tools do? I'm glad you asked. The model training tool helps developers train ML models on their data using different algorithms. The model deployment tool helps developers deploy ML models to production with a number of different deployment options. The model monitoring tool helps developers monitor the performance of their ML models in production using a dashboard and a number of different metrics. Lastly, there's Gemini, a multimodal AI model. Unlike traditional language models, it's not limited to understanding text alone. It can analyze images, understand the nuances of audio, and even interpret programming code. This allows Gemini to perform complex tasks that were previously impossible for AI. Due to its advanced architecture, Gemini is incredibly adaptable and scalable, making it suitable for diverse applications. Model Garden is continuously updated to include new models. And now you know absolutely everything about generative AI. Okay, maybe you don't know everything, but you definitely know the basics. Thank you for watching our course, and make sure to check out our other videos.
All right, 30 minutes of reading, baby. No, let's all right, let's do today's quote, and then we will fucking. Actually, that's not. AI BARD is a large language model, which is a type of machine learning that has become known for its ability to generate natural sounding language. That's why you often hear it described interchangeably as generative AI. As with any new technology, it's normal for people to have lots of questions like what exactly generative AI even is. To talk through common questions about generative AI, large language models, machine learning, and more, we sat down with Douglas Eck, a senior research director at Google. Doug isn't only working at the forefront of AI, but he also has a background in literature and music research. That combination of the technical and creative puts him in a special position to explain how generative AI works and what it could mean for the future of technology and creativity. Here's what he had to say. Before we dive into generative AI, we have to talk about AI more broadly. It's one of those intriguing but I just poked my eye, but often nebulous kind of term. What exactly is AI? AI is a broad term often used to describe all sorts of advanced computer systems. I prefer to talk more specifically about machine learning. Most of what we see in AI today is really machine learning, endowing computer systems with the ability to learn from examples. We call machines programmed to learn from examples neural networks. One main way they learn is by being given lots of examples to learn from, like being told what's in an image. We call this classification. If we want to teach a network how to recognize an elephant, that would involve a human introducing the network to lots of examples of what an elephant looks like, tagging those photos accordingly. That's how the model learns to distinguish between an elephant and other details in an image. Language models are another type of neural network. How do language models work? Language models basically predict what word comes next in a sequence of words. We train these models on large volumes of text so they better understand what word is likely to come next. One way, but not the only way, to improve a language model is by giving it more reading or training on more data. Kind of like how we learn from the materials we study. If you started to type the phrase Mary kicked a language model trained on enough data could predict Mary kicked a ball. Without enough training, it may only come up with a round object or only its color yellow. The more data involved in training the language model, the more nuanced it becomes, and the better chance it has the insight to know exactly what Mary is most likely to have kicked. In the last several years, there have been major breakthroughs in how we achieve better performance in language models, scaling their size to reducing the amount of data required for certain tasks. Hey, what's up, Andrew? Got it. So we've defined AI and language. What about generative AI? A generative model can take what it's learned from the examples it's been shown and create something entirely new based on that information. Hence the word generative. Large language models, LLMs, are one type of generative AI since they generate novel combinations of text in the form of natural sounding language. We can even build language models to generate other types of outputs, such as new images, audio, and video, Imagen, Audio LM, and Finicky. This brings a big question a lot of people have. What does generative AI mean for creative fields and creativity in general? Alright. Wow, this shit's fucking annoying. Let me move this fucking tab. Alright, let's do, if I do Control W, it's gonna fucking, let's open new window. Let's do the dun 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 dun. Oh my stomach is killing me, man. Holy shit. A lot of people are taking offense to that shit. Clearly there are opportunities here, but what about potential challenges? I raised 2 kids and got a literature degree before I went into computer science, so I'm asking myself real questions about how educators measure success in a world where generative AI can write a pretty good 8th or 9th grade essay. If you think back when the graphing calculator emerged, how were teachers supposed to know whether their students did the math themselves? Education advanced by understanding what tools students had at their disposal and requiring students to show their work in new ways. Companies, including ours, have a responsibility to think through what these models report and how to make sure this is an evolution rather than disruption. I'm glad you brought up responsibility. Can you talk about how Google approaches developing machine learning? We are and have been taking our time to do this thoughtfully. If we build a project, we want it to be confident it can be helpful and avoid harm. In 2018, we were among the first companies to develop and publish AI principles. Okay, so they want to... Oh, shit's so fucking bullshit. Bullshit, bullshit, bullshit. Build generative AI search and conversations for customers and employees with AI Vertex search. Conversation formerly Gen App Builder, now generally available. I gotta pay for that shit. Key features, Vertex is out of box. I'm not paying for that shit. Alright, let's see what we got here. Free trial credits. I'm trying to make my own shit, bro. I'm not trying to fucking... Alright, you can hold that, bro. I'm not trying to do that shit. If it comes down to it, I will pay for it, but I don't think I need to right now. What is generative AI? This was a year ago. Generative AI describes algorithms such as ChatGPT that can be used to create new content, including audio, code, images, text, animations, and videos. Recent breakthroughs in the field have the potential to drastically change the way we approach content creation. Yes, sir. Yes, sir. Generative AI falls under the broad category of machine learning. 45 terabytes? Dude, no, it's not that. It shouldn't be that fucking hard, though. Why is it? That's to do it on that big of a scale. This is a general chatbot. A general purpose bot for your needs. Okay. Let's see. Turkey was garnished with whole lime set in a star bowl, which appeared to be guacamole. It's part ChatGPT, so I can basic algebra problems. What are the limitations of AI models? How can these potentially be overcome? Long tail effect of general. Okay. Enable unethical. Really? Oh, this is that good shit. This is that good shit. Wow, 9 pages. Fuck yeah. fast, man. I don't care what the fuck's happening. Okay, so yeah, they can do speech recognition, visual audio. Powerful, arbitrary parallel computation for a modest number of steps. They can do arbitrary meaning fucking whatever. Parallel, maybe, I don't know. Computation, so math, for a number of steps. An example of the power of DNNs is their ability to sort n-bit numbers using only 2 hidden layers of quadrant. What the fuck? So while neural networks are related to conventional statistical models, they learn an intricate computation. Whenever the labeled training set has enough information to specify it. Thus, if there's a parameter setting of a large DNN that achieves good results, supervised backpropagation will find these parameters and solve the problem. Despite their flexibility and power, sensibly encoded with vectors of fixed dimensionality. It's a significant limitation since many important best with sequences whose lengths are not a known priori. Sequences pose a challenge for DNNs because they require the dimensionality of the inputs and outputs is known as fixed. In this paper, we show that a straightforward application of long short-term memory architecture can solve general sequence-to-sequence problems. The idea is to use one LSTM to read the input sentence one time step at a time. To obtain a large fixed dimensional vector representation, I'm reading and not understanding. Okay. The input has to be known and fixed. So it has to, the DNN needs to know what the fuck is getting into it and needs to know what is getting out. The idea is to use one LSTM to read the input sentence one time step at a time. What the fuck is that? And then use another long short-term memory architecture to extract the output sequence from that vector. Figure 1. Here's figure 1. The second LSTM is essentially a recurrent neural net model, except that it is conditioned on the input sentence sequence. The LSTM's ability to successfully learn on data with long-range temporal dependencies makes it a natural choice for this application due to the considerable time lag between the inputs and their corresponding outputs. Is the OS end of stream? There have been a number of related attempts to address the general sequence-to-sequence learning problem with neural networks. One approach is closely related to Kalkbrenner and Blunsum, who were the first to map the entire input sequence to vector, and is very similar to Cho et al. Graves introduced a novel differentiable attention mechanism that allows neural networks to focus on parts of their input. An elegant variant of this idea was successfully applied to machine translation by Badenau et al. The connectionist sequence classification is another popular technique for mapping sequences to sequences with neural networks. Although it assumes a monotonic alignment. Oh my goodness. I don't think I'll ever understand this shit. Our model reads an input sentence ABC and produces WX. Okay, so this is end of string. The model stops making predictions after outputting the end of sentence token. Note that the LSTM long short term memory. What the flip? Alright, now let's search long short term memory architecture. Wikipedia. Long short-term memory network is a recurrent neural network. Now we need to Google recurrent neural networks. A recurrent neural network is one of the two broad types of artificial network. Okay. Characterized by direction of the flow of information between its layers. In contrast to the unidirectional feed-forward neural network, it is a bidirectional artificial network, meaning that it allows the output from some nodes to affect subsequent input to the same nodes. It allows the output from some nodes to affect subsequent input to the same nodes. Their ability to use internal state memory to process arbitrary sequences of inputs makes them applicable to tasks such as unsegmented, connected, handwriting recognition, or speech recognition. The term recurrent neural network is used to refer to the class of networks with an infinite impulse response, whereas convolutional neural network refers to the class of finite impulse response. Both classes of networks exhibit temporal dynamic behavior. A finite impulse recurrent network is a directed acyclic graph. So now let's see what directed acyclic graph looks like. In mathematics, particularly graph theory and computer science, a directed acyclic graph, DAG, is a directed graph with no directed cycles. Okay. Directed graph is a graph that's made up of a set of vertices connected by direct edges, often called arcs, such that following those directions will never form a closed loop. A directed graph is a DAG if and only if it can be topologically ordered. What the fuck does that mean? Oh, hey. Topological ordering of a directed graph is a linear ordering of its vertices such that for every directed edge, UV from vertex U to vertex V, U comes before V in the ordering. In computer science, a topological ordering of a directed graph is a linear ordering, from one by one, right? Such that for every directed edge UV from vertex U to vertex V, U comes before V in the ordering. The vertices of the graph may represent tasks to be performed, and the edges may represent constraints that one task must be performed before another. This application of topological ordering is just a valid sequence for tasks. Precisely, a topological sort is a graph traversal where each node B is visited only after all its dependencies are visited. A topological ordering is possible if and only if the graph has no directed cycles. That is, if it is a directed acyclic graph. Algorithms are known for constructing a topological ordering of directed acyclic graph in linear time. Topological sorting has many applications, especially in ranking problems, such as feedback argument. Topological sorting is possible even when the DAG has disconnected components. The canonical application of topological sorting is in scheduling a sequence of jobs or tasks based on their dependencies. The jobs are represented by vertices, and there's an edge from X to Y if job X must be completed before job Y can be started. When washing clothes, the washing machine must finish before you put clothes in the dryer. Topological sort gives them an order in which to perform jobs. A closely related application of topological sorting algorithms was first studied in the 1960s in the context of the PERT technique for scheduling in a project manager. In this application, the vertices of graph represent the milestones of a project. Computer science, applications of this type arise in instruction scheduling, ordering of formulas, cell evaluation when recomputing formula values in spreadsheets, logic synthesis, determining the order of compilation tasks in order to perform in makefiles, data serialization, resolving symbol dependencies in linkers. What the fuck? The usual algorithms for topological sorting have a running time linear in the number of nodes plus the number of edges. Asymptotically, O plus absolute value of V, absolute value plus absolute value of E, which is vertices and edges. Remove a node from S are empty lists that will contain the sorted elements. While S is not empty, do remove a node from S, add N to L. For each node M with an edge E from N to M, do remove edge E from the graph. If M has no other incoming edges, then insert M. Oh wow, depth first search, hell yeah. If the graph is a directed acyclic graph, I still don't even know what it is. Otherwise, the graph must have at least one cycle, therefore topological sort is impossible. Reflecting the non-uniqueness of the resulting sort, the structure S can be simply a set or a queue or a stack. Depending on the order that nodes N are removed from the set S, a different solution is created, a variation of Kahn's algorithm that breaks ties lexicographically. Using the alphabet. Forms a key component in the Kaufman-Graham algorithm for parallel scheduling and depth first search. An alternative algorithm for topological sorting is based on depth first search. The algorithm loops through each node of the graph in an arbitrary order, initiating a depth first search that terminates when it hits any node that has already been visited since the beginning of the topological sort, or the node has no outgoing edges. Empty list that will contain the sorted nodes while exist nodes without a permanent mark, do select an unmarked node N. Visit N. This is the function. Visit. If N has a permanent mark, then return. So these are the base cases. If N has a temporary mark, then stop. What's the difference between stop and return? This graph has at least one cycle. What is a cycle? What is a cycle? Graph, theory, cycle, definition. A cycle in a graph is a non-empty trail in which only the first and last vertices are equal. A directed cycle in a directed graph is a non-empty directed trail in which only the first and last vertices are equal. Motherfucker, bro. I have so much to catch up on. The algorithm moves through each node in an arbitrary order, initiating a depth first search that terminates when it hits any node that has already been visited since the beginning of the topological sort, or the node has no outgoing edges, i.e. a leaf node. Empty list that will contain the sorted node. While exists nodes without a permanent mark, do select an unmarked node, visit N. Mark n with a temporary mark. For each node m with an edge from n to m, do visit m. So it goes through each one, and now m is now a node. Let's bring up fucking feet on this bitch. So then it goes to m, but now m is now the fucking n. So it goes to the next one, then the next one, and then the next one, and the next one. Remove temporary mark from n. Mark n with a permanent mark. And then it still needs to run these parts. So when it starts visiting, so on that last portion, it'll remove temporary mark from n. It'll make n have a permanent mark. And then n is added, so that node is added to the head of L. L is an empty list that will contain assorted nodes. And then it keeps going, it keeps going, it keeps going. Each node n gets prepended to the output list L only after considering all other nodes that depend on n. Specifically, when the algorithm adds nodes n, we are guaranteed that all nodes that depend on n are already in the output list. They were added to L either by the recursive call to visit that ended before the call to visit n, or by a call to visit. It started even before the call to visit n. Since each edge and node is visited once, the algorithm runs in linear time. This depth-first search-based algorithm is one described by Gorman et al. It seems to have been first described in print by Tarjan, 1976. Okay, so now we're on parallel algorithms. In a parallel random access machine, a topological ordering can be constructed in O log n O log n quantity squared time, using a polynomial number of processors, putting the number into the complexity class n squared. What the fuck is that? Another fucking rabbit hole. Next class. Alright, looks like it. Set of decision problems decidable in polylogarithmic time. A parallel computer with a polynomial number of processors. In other words, a problem with input size n is in NC if there exists constants c and k such that it can be solved in time O log n quantity to the c using O of n to the k parallel processors. Stephen Cook coined the name Nick's class after Nick Pippinger, who had done extensive research on circuits with polylogarithmic depth and polynomial size. Just as the class P can be thought of as the tractable problems, Kalbam's thesis, so NC can be thought of as the problems that can be efficiently solved on a parallel computer. NC is a subset of P because of polylogarithmic parallel computations. But most researchers suspect this to be false, meaning there are probably some tractable problems that are inherently sequential and cannot be significantly sped up by using parallelism. Just as the class NP-complete can be thought of as probably intractable, so the class P-complete, when using NC reduction, can be thought of as probably not parallelizable, or probably inherently sequential. The parallel computer in the definition can be assumed to be a parallel random access machine, PRAM, that is a parallel computer with a central pool of memory. Any processor can access any bit of memory in constant time. let's keep going. Let's keep going. As with P, a slight abuse of language, one might classify function problems and search problems as P. C is known to include many problems, including integer addition, matrix multiplication, greatest common denominator, reduction to linear algebra. Often algorithms for those problems had to be separately invented and could not be naively adapted from well-known algorithms, Gaussian elimination and Euclidean algebra. Let's see that. Is that I wonder if that works with Gaussian. Holy fucking shit, that's how this shit plays out. Oh my fucking god, this is just linear algebra. That's fucking wild. Does Gaussian blur? Okay, so they come from different mathematical. A smarter version of me will understand that. understand. Now I understand. So we are given an m by n matrix. Into a matrix in row echelon. The following pseudocode Aij denotes the entry of the matrix A in row I in column J with the indices starting from 1. This transformation is performed in place, meaning that the original matrix is lost for eventually being replaced by its row echelon form. Okay, so that, okay, all right, finally we're in parallel. Oh, okay. Initializes a set of local vertices with in degree. What in the world is in degree? In degree and out degree. For a vertex, the number of head ends adjacent to a vertex is called the in degree of the vertex, and the number of tail ends adjacent to a vertex is out degree. Let G equal V and A, and V is all of the numbers in big V. The in degree of V is denoted degree V, and its out degree is denoted deg plus V. A vertex with degree V is called a source, as it is the origin of each of its outcoming arcs. Similarly, a vertex with degree plus V is called a sink, since it is the end of each of its incoming arcs. The degree sum formula states that for a directed graph, for every vortex V inside V, dig plus V minus V, the graph is called a balanced directed graph. Gotta go pee.